Welcome to the seminar today. We are pleased to have invited our alumni, uh, Philip Pegion. Okay.
Yeah, you got it.
He graduated from here in 1996. He's the deputy director of the modeling data simulation division in NOAA, which is a physical science laboratory located in Boulder, Colorado. Um, Today, he will speak about the new topic prediction system in NOAA based upon the unified forecasting system. So let's welcome Philip.
Hey, thanks, Peng. It's great to be back here. I graduated in '96. I took a class in '97 and came back once in like 2003 to visit, and haven't been here in almost 20 years. The nice thing is that it looks like this building down here hasn't changed, but I guess that's not really a nice thing. Well, thanks for coming, everybody. Today I'm going to talk about coupled modeling, and I'm working in NOAA on the research side, working closely with the Weather Service, and we're basically working on developing a fully coupled prediction system, and it's based on the unified forecast system, which I will go and explain what that is if you don't know. So the introduction is that the Weather Service has been producing global numerical weather predictions since 1974, the year I was born. So it's been a long time. But over the years, the models have increased in complexity, and models have evolved independently based on their target application. So there's these regional model, small scale modelings like the RAP, the RUC, the HER, HWRF, the hurricane model that have basically evolved out of the WRF model, which is the weather research and forecasting model developed by NCAR and the community. And while it's the medium range forecast, so like out to days 10, out to even days 16, were based on the GFS and the global ensemble forecast system, were developed around a global spectral model. And more recently, the global modeling effort has been moved to a new model that's now called the UFS. You might have heard the terms the FE3, FE3 GFS. FE3 is just the dynamical core piece of that. The UFS is the whole umbrella that contains many different pieces of it, all within the system. And then just continue on as the background is that each model grew more and more complex. There's just been a growing need to consolidate the modeling efforts across these different timescales. And because the National Weather Service is making predictions from minutes to months, ranging from the water forecast system to the climate forecast system. So wide range of applications. And this slide is supposed to scare you. It scares me. This is the current state of modeling in the operational framework of the Weather Service. So each of these pieces is a different forecast. Like top up there is a climate forecast system, which I'll talk a little bit about. There's a hurricane model. There's the global spectral model. There's all these different pieces of data simulation, and they all depend on each other. There's this crazy quilt of how things go together and depend on each other, and it's kind of overwhelming. If you want to change one piece, every other thing is dependent on it, and they all are different. So you need expertise in each system. And there's been review panels for many, at least 10, 15 years saying that we need to streamline this system. And so the goal is to have something that's a little more, less scary. There's focusing on the predictive time scales from the hours or even minutes to 1 hour forecast system all the way up to the seasonal forecast system. And then there's forecast targeted on day 5, weeks 2, 1 month or so. And there's also different targeted phenomena. Like there's a special modeling effort on hurricanes. There's a space weather effort focusing on the thermosphere and how satellites interact with solar flares. Then there's marine coastal application. There's air quality, and then there's also flood and hydrological modeling that spans many of these timescales. But today I'm going to just focus on the pieces that are in this gray, in this purple, this pink box that are basically focused on the actual, I call it the forecast modeling, that are focused on a time scale and not a specific target of like a hurricane, even though I will show results from that. And more specifically, my background, my expertise is more in the longer range predictions. of the months to year timescale. So just go over quickly on what the unified forecast system is. Just look at this right box here. It's a multiple component system that has an atmosphere model that also includes a land model in there. There's an ocean model, there's a sea ice model, there's a wave model, there's an aerosol chemistry model that interacts directly with the atmospheric model, and there's this thing in the middle called mediator that allows these different components to talk to. Because they're all operating on their own time scale, they have their own native coordinate system, their own units, so you need something that does the communications between them. And also, the way you work on computers is that you have, the first 100 or so processors are working on the atmosphere, the next 100 are working on the ocean. So you need to actually have communication across the different parts of the computer. And just a little background is, so focusing on the global applications, that currently there's 3 global models running operationally at the Weather Service, focused on different timescales. So there's the GFS, which is the high resolution model, deterministic forecast, and it runs out to 14 days. Actually, I thought it was 16 days. But it's uncoupled right now. It's just atmosphere only. You just persist the initial sea surface temperatures and you run forward. And then targeting a little bit of a longer time scale is the global ensemble forecast system that runs out to 35 days. And again, it's an ensemble, so at the initial time, you sample the uncertainty in initial conditions and run forward, so you have basically a probability density function of your potential outcomes at these longer time scales. Because once you get past like day 10, forecasts shouldn't really be deterministic anymore, because the chaotic errors in the atmosphere grow, and you have to basically go to a probabilistic forecast. And that system is not coupled. Again, it's basically being forced with sea surface temperatures that are actually now, at least they're predicted. They are taking them from CFS2, which is the model below I'll talk about briefly. So it's using a sea surface temperature forecast, so the sea surface temperatures can evolve over the 30 days, but there's no interaction between the atmosphere and the ocean. And then lastly is the CFS version 2, which is now a 12-year-old model that's still running. This is fully coupled atmosphere, land, ice, and ocean. And it runs a 9-month forecast. It's lower resolution. And again, it has ensembles, because this longer time scales, we need probabilistic forecasts. And it's using the old spectral model. Again, the model actually itself is from 2009. So it's very old. And then this blue is basically the plans of upgrading these forecast systems. So the GFS will go to version 17. That is about another year and a half out. And the GEF version, version 13 is still, these are both still in development stages right now, with the expected upgrade to happen in about a year and a half or so. And then the seasonal forecast system, version 1, which will replace CFS version 2, is the project that's actually just getting started, and it's going to be like a 5-year process of getting that model ready to replace CFS2. So I'm going to talk a little bit about like, why do we need a fully coupled model instead of just having an atmospheric model. And so air-sea interactions play an important role at the longer lead times. And I can talk about that a little bit more. It's also for, I said I was going to talk about targeted phenomenon. It improves hurricane forecast predictions, because there's strong fluxes in a hurricane. A hurricane's going to cool the sea surface temperatures, which would then weaken it behind. Then there's a lot of interactions going on there. So you can't just assume that the ocean has an infinite resource. And overall, having a coupled model forces you to get the right answer for the right reason. You can't just hide your problems in a boundary condition that's never going to feed back. So the trade-off is that it really exposes all our problems. So in the short term, makes things worse, but it's going to force you to make a better model. And at the European side, they actually seen improvements in their one-day forecast when they went coupled, just because these physical processes are better represented. And on the right, it was just a little schematic, basically sort of showing the importance of each of these components at different time scales. So at your forecast of what's going to happen this afternoon or for tomorrow, the atmosphere contains most of the information. We don't really care about the state of El Nino or what the sea ice is doing for tomorrow's forecast. Because that information is already baked into the atmosphere that will get here tomorrow. But as we go with these longer leads, we need to know that information because there's information that propagates over the globe over a couple weeks or even longer. So these other components of the land and the ocean are relatively more important as you go through these longer time scales. And, oh, sure.
Do you recall when the European Center for Global Climate Model?
I don't know the date exactly. I want to say it was like 4 years ago, but I'm just guessing at this point. So,
Okay.
Yeah. So this is just sort of just a little more motivational why we care about coupling, and this is just from the hurricane forecast model, which is the same atmosphere model, same ocean model, just run at a higher resolution and slightly configured differently. But this is showing Hurricane Laura going through the Gulf of Mexico and it's leaving its cold wake behind. And then for other things like one of these physical processes, that even at the local grid point, there is a relationship between precipitation and sea surface temperatures that's out of phase, where think about the sea surface temperatures will warm up. That will increase the humidity in the boundary layer. You're going to get convection. Convection is going to cool off the SSTs, and then it shuts down the precipitation, and you have this cycle. And you do not get that cycle in an atmospheric model with fixed SSTs. The SSTs won't cool off. And this is sort of showing, this is at different regions, but it's the lag correlation plus or minus 2 weeks, showing in the dashed line is the observations. So it has this nice signal that the sea surface temperatures about 10 days before your precipitation maximum are the warmest. And then as it starts raining, it cools off. And this is this is the CFS version 2 model. It shows that relationship somewhat. It's better in some regions, whatever. So that the couple model does capture this to a point. Now there's also room for improvement, but again, the point is you will not get this in an atmosphere only model. And this is a study that was looking at this in reanalysis. So this is now looking at each grid point over the tropics and mid latitudes, this instantaneous relationship between precipitation and temperature. And the top left box is the observations. And this shows that most of the regions, this blue means that at the point of where there's maximum precipitation, the SSTs are actually below normal. It's that there's the lead up of the sea surface temperatures, it starts raining in and the SSTs cool off. On the top right is their reanalysis, which is atmosphere only, and you don't have this relationship. It's actually the wrong sign. And the bottom left is when they actually went to a coupled reanalysis where they have the atmosphere and the ocean both interacting. And maybe it's too strong in this relationship, but at least on the right side. So the point is I just want to show that this relationship matters at many different timescales. So then I want to sort of go into, for these extended range predictions, what are we looking at? What are the targets, the products that Weather Service will produce? And this is not a full list. There are many other things that people are doing. But the main customers from the Weather Service is actually the Weather Service in their mind. I don't work for the Weather Service, I can say that. And really, I work closely with the Environmental Modeling Center. They're the ones who build the models. Climate Prediction Center produced the forecast at these timescales. So the Climate Prediction Center produces temperature and precipitation outlooks for weeks 2, weeks 3, 4 combined, weekly and monthly. And the top right there is just a picture showing an example of a forecast showing, that's a drought outlook, I apologize. The bottom right is a precipitation outlook showing above normal precipitation in the Pacific Northwest and the Great Lakes, and then dry in the South. So they make products like that, above normal, below normal, for different time scales. And they also do these monthly and seasonal drought outlooks, and that's what the top right panel is. It shows where there's existing drought, and then they show areas where drought may intensify or improve, or even develop. And then there's other outlooks that they do. There's a U.S. hazards, global tropical hazards, a seasonal hurricane outlook. They predict El Nino itself, and they also do Arctic sea ice prediction. These are the operational projects. There's also a lot of other applications that people in my laboratory are working on, such as like marine heat waves. They're looking at coastal inundation due to climate change. El Nino impacts have affects the sea level on the West Coast, storm surge modeling. There's many of other applications that people are looking at these timescales. So I want to talk a little bit about evaluating predictions at these S timescales. So traditionally in a weather forecast, this is the gold standard. It's the 500 millibar height anomaly correlation as a lead, as a function of time. So the x-axis is forecast lead going from your initial condition to day 0 out to day 10. Y-axis is the anomaly correlation. So the pattern correlation between the observed 500 millibar height anomalies and the forecasted. And if you're starting with the initial conditions that look like the actual atmosphere, the value is 1, and as you go out in time, that skill drops off, and that's why the anomaly correlation drops off. And I drew a line at 0.6 because that's generally considered what is useful skill. So in this figure, which is from several years ago, it shows about 7 days of useful skill in a forecast at this weather time scale. So if you extend this to a 35-day forecast, this is what you get. You get useful skill in this case out to day 10. It's a newer model, so it's a little better. But then once you get past day 10, the skill just sort of goes down flat. There's no useful skill if you look at any given snapshot. The thing I do want to point is that you notice the skill doesn't go to 0. It's hovering around 0.2. So this sort of shows that there is something in there that is not just random. If it was just a random forecast, no information, the skill should be 0. And there is something in there. And the trick is to find the pieces that are associated with that lower skill, in a sense of like there's multiple ways to go at it. One is, are there certain times when you have a forecast that will be skillful, which I don't really go into here, but that's called a forecast of opportunity. And this is grid point by grid point, day by day. When you go to longer leads, you're going to do a week average, you're going to do a month average, you're going to do some sort of time filtering to basically get rid of this small scale weather noise, and you're looking more like at the climate signal or some sort of regime signal. That might be a couple of weeks type of thing, like a MJO, blocking, so forth. So one thing is, like, in a modeling sense, we look at, there's a whole field of work that people working out there at looking at the sources of SS predictability. And this is just a schematic that came from the Modeling Analysis and Prediction Project SS Prediction Task Force that sort of just tries to lump in all of the different phenomena that people have studied and have linked to predictability at the sub-seasonal to seasonal timescales. That's what SS is. So there's like the stratosphere polar vortex breakdowns are associated with Arctic oscillation and cold air outbreaks, and the wave activity flux here feeds into that. There's the El Nino Southern Oscillation, there's the MJO, and it's associated with teleconnections. And there's all these gray lines sort of showing how they're all interrelated. There's the North Atlantic Oscillation that's blocking many different pieces. So the goal really is to look at, do our models represent these processes or these phenomena? And then try to improve those, and then we put it together in a prediction system. The intention is that improving the predictions of these and the representations of these will help us predict up the longer timescales. So, so one of the things we've done, now I'm going and finally getting to some model results, is that we ran long climate simulations of the unified forecast system. And we also compared it to the NCAR CESM2 model in a project. And just briefly, we ran a couple prototype tag 8 doesn't probably mean anything to you. It did for the meeting I presented this at. But it's one of the latest versions of the couple model that we had at the time. We're running a 1 degree resolution, and the horizontal is roughly 111 kilometers by 111 miles. And we ran 50-year simulations. And these are historical forcing. So going from 2000 to 2020, we had the observed CO2 changes. And then after 2020, it was just fixed to the 2020 values. So looking at climate change in these runs is not like, you don't want to do that. And I don't want to go into the details here too much, but I ran two different versions. One is what called deterministic physics. That is basically what the GFS uses. And then we, for the ensemble, we add in these other physical parameterizations called stochastic physics that is supposed to represent the model uncertainty. And the point of there is that it injects more noise into the model. So we have a spread that better represents the uncertainty in the model on these medium range timescales. And the project really was focused on the impact of the stochastic physics, CESM, very similar configuration, 1 degree, their CMIP version, because that model is designed to be a climate model, runs a little faster, they were able to do 100-year runs, not 50-year runs. But again, they used a different, they ran their deterministic CMIP 6 physics, and then they added in one of the stochastic schemes called SPPT. And just quick, some of the results here is that, so the top panel is observation. So what we're looking at is the annual mean sea surface temperature and how it varies over 50 years. So it's the standard deviation over time at each grid point. And the top left and right are two different observation estimates and over different periods. So the left one is actually 100-year time. It's 100 years of observation from the RSST, and the right is only the last 40 years. So it sort of shows like more of the modern period where you have better observing system. In this case, they're very similar. If you look at some other metrics, there's differences between the two. And then on the middle row is the UFS model, and then the bottom is CESM. So the take-home point here is that the UFS, when you just run it out of the box, which is the left one with the deterministic physics, is actually missing a lot of the variability in the tropical Pacific associated with El Nino. And then we add in the stochastic physics, we're injecting more noise, and we're getting something that might be a little stronger than observations, but it's definitely an improvement. And the bottom is the CESM doing the same thing, and their differences between the two really aren't that different. But then the things that we care about living on land is more precipitation and temperature impacts on land. And this is going to just sort of show what the precipitation variability looks like in the same time scale. So again, the left is, when here the time frames are actually flipped. I have not labels wrong. The left is a modern record, the satellite record. So you have precipitation over oceans. The right is station data over land, 100+ years, but it's only over land. So it's hard to see the big picture. But just like in the previous one, the tropics don't have enough variability in the left run, the deterministic physics, where you get more there. But the thing I did want to highlight, which is probably hard to see from there, is that the the variability over along the Pacific, like over the California coast and the mid latitudes, actually matches observations quite well. So if this is in the sense that we can represent these large scale features that change year to year in a statistical sense. This doesn't say we could predict it, it's just say that we could produce these statistics. And then more focused on now on El Nino, this is now looking at a composite of the El Nino events in the different simulations. And here again, similar to the total variance, the standard deviation plots I was showing, the UFS with the stochastic physics on the right is a little too strong, but the teleconnection, so that is the pattern I'll point out here. So there's like here, so you have those warm sea surface temperatures here, you have the cold above it, and then you have this warm area over Western Canada, and then more cold here. That's basically this wave that's coming out is actually well represented in this model. So this sort of suggests that if we're able to predict the El Nino, we're going to get the resulting circulation changes in mid latitudes. And then just looking at the El Nino evolution itself, and this is where another thing where I think this the UFS is actually doing quite well. So I'll explain this plot here. So now we're looking at a cross section along the equator. So this is longitude going from just off the Philippines to the coast of Peru, and then this is time going down. So you start here in the composite sense, you go down. And so this, again, this is the two observed estimates based on different time scales. So you start typically before the El Nino happens, it's slightly cool, and then the El Nino SSTs increase throughout the fall, and then peak in the late fall, according to this picture. And then for the UFS, it's the El Nino is weak, so it doesn't have much going on, and then it's better in this run, and this for just comparison to CESM. The thing I do want to point out that I thought was very exciting is in nature, typically you have an El Nino, it happens, it goes away. La Nina is typically, not typically, but a lot of times happen successive. You have a La Nina last year, you got one this year. Like we just came off a 3-year La Nina. So the cold events tend to be longer lasting. And you see that in the observations here where you have cold preceding cold. And you actually are starting to see that in the UFSPA. So the UFS model is getting this tendency of having a multi-year La Nina. And this is the first time I've actually seen the model do this. So I don't know if it's a fluke, but I was really excited about that. So that was the good. Here's the bad. This is now looking at the trend. I said, we shouldn't really be looking at this for climate change studies, but there still should be still things to look at. So top is now the trend in the sea surface temperatures. Over the left one is 100 years, again, the right one is 40 years. So you're seeing the global warming signal in the observations. The bottom one, I'll skip UFS for a second. The bottom one is the CESM. This is from their pre-industrial control run, which has no climate change in it. So it's basically just pre-industrial values held constant. So you shouldn't be seeing a trend in it. And for the most part, you don't. On the left side, it might be that there could be like a interglacial oscillation, like a PDO or something going on there. But there isn't no global warming signal there. UFS, this is where the work needs to be done. The southern hemisphere looks like it's warming, like observations, but the northern hemisphere is cooling. So this is an issue we need to address.
Yeah. Why are you looking at pre-industrial control?
I did not set up that experiment. My colleague at NCAR did, and I don't know why.
That's what you'd want to see how similar the trend is.
Yeah. Yeah. I mean, the left, the CMX, they have that for the CMX 6 run, the one on the bottom left. They have that for the whole. They have that for projections, the historical, everything. When this was a sensitivity experiment for stochastic physics, ultimately, she wanted to have something that the background wasn't changing, I think.
So both the left and the right and the bottom for industrial control.
Yeah. So I probably should have cut them off on this plot, but yeah, the model's a difference. But my editor's plot, because I didn't want to show everything is great. But in the study, we're focusing on things that are on shorter timescales.
So in the middle row, though, you expect or hope for a warming trend.
I would expect that a warming trend goes, well, at least in that run we had the CO2 changed for the first 20 years, and then it was held constant because we ran out of the observations and we didn't use a projection. We should have, but we didn't. So I would expect, at least not be cooling in the northern hemisphere.
CO2 is held constant in the middle?
It's the first 20 years it's increasing with observations, and then it just is held constant after 2020. So it's ramps up and then held steady.
For the last 30 years.
Yeah, exactly. Yeah. Unfortunately. So I just want to show that there is still work to be done. But then these are the things that were more targeted in these experiences, looking at higher frequency variability. So what I'm showing here, I'll familiarize, this is called a wave number frequency diagram. So you take the precipitation from the model and you average it in a band around the equator, and then you do compute Fourier transforms on it in space and in time. And this sort of breaks out the different wave numbers along the x-axis. So the 0 line is in the middle, so that would be a wave number 0, so your mean value. And then on the right is wave numbers 1, 2, 3, 4, all the way up to 20. And right on side indicates features that are propagating towards the east. And on the left side are your negative wave numbers. Those are features that are propagating to the west. and then the y-axis is the temporal frequency, whereas the bottom being basically the length of the integration, or the longest wave number you could time scale you could compute in a Fourier transform, and then it doesn't fully show the whole range, but it goes from I don't know what the bottom is. So it's basically your mean all the way up to, I think it's a 2-day cycle. So it just keeps on going higher, higher frequency. And this is something that the models typically have struggled with, is this connection between these different temporal and spatial scales. And the bottom is ERA 5, and the bottom right is actually a satellite estimate of precipitation. So that's what we're aiming for, because even there, ERA5 is considered very good as precipitation. And for the most part, it matches this I-merge, but it's not still one-to-one correspondence. And the thing I just want to point out is this big blob here. These is what we call equatorial Kelvin waves in the atmosphere. And this blob at the bottom is this representation of the Pegion oscillation. So the stochastic physics, again, produces more variability than deterministic physics. So here it's like we are getting the signal of an MJO. It's maybe a little too, it's weaker, but it shows something there. And then it has this propagation in the Kelvin wave that is pretty important. And then this is more going into a higher standard. This is actually the coherence now. This is looking at the connection between the precipitation and convergence. And here, the model actually does pretty well, where these arrows also show the phase. So these arrows that are going down to the right there indicates that convergence is out of phase with precipitation, which you expect that it'd be, divergence. So divergence is out of phase with precipitation. You expect convergence when it's precipitation, but it's not. If it was pointing straight down, that would mean they're in phase. They would directly out of phase. But this arrow leading a little bit means that the convergence actually leads to precipitation, which, you get your convergence and then it rains. That's basically what it's saying. And again, this just shows that how it works on different time scales. So this is, I would say, a good result. And then the next slide is, I didn't point out, this is actually at 850 millibar height. So basically more like the base of the cloud layer over the tropics. This is now at the top of the atmosphere, like top of the thunderstorms, like at the anvil layer, where divergence is happening. In this case, things break down. So in the observations on the bottom, you're getting divergence where you're getting the precipitation. The model's missing that. So that's another area that the developers need to work on. And basically, we're getting the convergence, we're getting the precipitation, but we're not getting the divergence aloft, which will have effects downstream. Basically, we won't have this Rossby wave source to then project into the extratropics and impact your mid latitudes. Then just looking at a couple other things. This is we care about, especially in the subseasonal range, like we 3 or 4, you care about blocking. So you could have a block setup like we had this summer over Canada that lasts for a month and affects the weather over a large area. And blocks are fairly predictable once they establish, but the models typically don't do blocking too well. So what I'm showing here is these black lines are 2 observed estimates of a blocking index. And the blue line is it's CAM. I think it says CAM 5, so it's not CESM. It's the atmosphere only version. And the purple one on the left is the UFS. I don't have CESM anymore. I didn't have the daily output for there because this is based on daily data. And then the right is with stochastic physics. And the take-home message here is that this model actually is doing blocking pretty well. Usually models typically are weak on the blocking. This one's a little too strong. But it's it's something we can improve on, but we're overall pretty happy with this. And then, so that was, again, just this long simulation. Now I'm going to talk briefly about initialized predictions. So now getting away from just what the model actually does on its own versus how is it doing prediction. So we've done a lot of testing with the UFS in retrospective forecast up to 35 days. So targeting weeks 3, 4, the subseasonal part of S to S. And these runs were done at a quarter degree. I'll try to speed up a little because I realize I'm getting long here. And the first thing we looked at is our forecast of the Medellin-Juliet oscillation. And this is just like a benchmark. How do we do? And the black line is the current operational system. So this shows, in this case, the dash line is at 0.5, but it's showing, in that case, a useful skill out to like 22 days. Whereas the latest version of the model we have has useful skill now at 25 days. So this is a big improvement in our skill of the Medellin oscillation. And again, these are limited sample forecasts. I think they're only 7 years of initialized predictions. Oh, sorry, it's only 2 years. Sorry, this goes, my bad. But eventually we're going to run a whole free forecast data set. We'll have 30 years to do more robust statistics. And then other things that we're looking at is sea ice prediction. And so this is actually not a forecast skill, but this is showing the model's bias. If you look at it closely, the top row is June, July, August, so northern summer, looking at the Arctic Ocean here, and the bottom is the fall. So it's the melt season and then the freeze up season we're looking at here. And what I'm showing here is the June, July, August mean for different lead times. So I'm not looking at the variability year to year, but the point here is that if you look across the top, the week 4 forecasts have less ice in them than week 1. So the model has a tendency to melt out the ice on its own, that it shouldn't be more than it's melt than it should be. And on the bottom is the opposite. If you look, the week 4 forecasts have a lot more ice. So basically there are biases in the model that will impact the skill of forecasting it. So these are things we're looking at, and we're trying to address these things through various ways of looking at cloud properties over the Arctic Ocean, how it interacts with radiation, and so forth. And then we're also looking at basically air-sea interactions. So the plot here on the left is it's deducing the upwelling in the ocean based on the curl of the wind stress. So on the left area is basically the climatological upwelling in the colors from the ERA5, and the arrows are the mean wind stresses zoomed in along the tropical oceans. And the top right is they did a set of experiments, retrospective forecast, and looking at the bias in the upwelling compared to ERA5. And it's a pretty large bias. There's way too much upwelling just off the equator in the Pacific, and even and then there's actually downwelling south. So the arrows are the wind stress biases. So really big bias here. And so they initialized the model with this ocean analysis that the Climate Prediction Center produced. The bottom row is they redid the experiments with ocean initial conditions based off of ORIS-5, which is an ocean reanalysis that the European Center has produced. And everything else is the same. This bias pretty much went away. So, and this is a week 3-4 forecast here. So even with the just changing the ocean conditions, you're reducing your bias out 3-4. So the take-home message here is the ocean has a lot of memory, and we really need to pay attention to what's going on there when we have a couple models. Really how it's even improving the wind forecast. So then going into the longer time scales, this is where things are a little more limited samples, and just like with ongoing still is that we're looking at seasonal prediction experiments. And these are very limited. It's a mix of a 0.5 degree and 1 degree experiments, and we're going to lower resolution because we have to run a 9-month forecast instead of a couple weeks, so it just takes a lot more compute time. So you go to lower resolution to get it done in a reasonable amount of wall clock. And for these experiments, we've done only one initialization once per year, but over multiple years. And they have a 5-member ensemble to capture the internal variability. And the first thing I want to point out, and so this is these are experiments done at the 0.5 degree from a colleague, Sharon Sun, that looked at, this is the tropical mean sea surface temperature. So she's looking at just like a bias, not really looking at skill or anything like that. The black line is observations, and each box here is a different year. So she did 6 different experiments with different years, and the black line is observations, and the red line is 2 different configurations of the. It's the same version of the model, two different initial conditions. Just like in this slide here, I showed the impact of different initial conditions. She's looking at that in the seasonal sense. Again here, so the model has a warm bias, and pretty much all of these runs, the colored lines are above the black. That means the model's too warm. The black line, sorry, the red line is the industrializations that are produced, the ocean conditions are produced by CPC, and the green is from the European Center's initial conditions. So again, even there's a lot of memory in those ocean initial conditions, because if you look at, like, for example, for these, how the green just stays above the red. So again, the ocean has a lot of memory that we need to account for, and we need to get the initial conditions as close to truth as possible. And the thing I want to point out here is that if you look in the beginning of the forecast, that they look very similar, but then over time the RS5 ones are warmer, and that is basically reflected in what's going on in the subsurface. Now what I'm looking at is cross sections along the equator, so longitude depth down to like 220 meters. And now this is the difference just in the initial condition between the two versions of initial conditions. And this is showing that the CPC product, the one that ultimately is cooler, even though the sea surface temperatures are the same at the start, are cooler in the subsurface. And that information stays around for months. So we really need to be looking at what's going on below the surface. And then this is now basically looking at the this was the these initial conditions, and then these are what the forecasts look like at 3 months. So it's like every case you see more reds than blues, and the top row is the CPC based ocean initial conditions. The bottom is RS5. So again, they both are warm compared to observations. But this sort of shows you like underneath what's going on. And again, they're both warmer. I was also amazed at how similar they were in this sense. Like, look at 2014, both initial conditions have this warm blob there. So even though I'm trying to say with this, even though there are differences, there are different evolutions, there's certain aspects between the descriptions that are just going off in the same direction, and it's not where observations went. So this is where, again, these are ensemble means, but basically looking at the uncertainty around the ensemble forecast will help you basically hopefully have less forecast errors. And then this is just another way to look at it. This is now the 1 degree version of the model, but similar setup, initialized once a year. And this is looking at skill maps across the whole global oceans. And the left figure is 6 panels, is the UFS 1 degree, and this is comparing, just pulled off of NCEP's website, is the forecast skill from CFS2. So this is very preliminary, and we tried to match the color bar. The point out, and then the top left is it's the first month, then it goes the second month forecast, lead time, 1 month, 2 months, 3 months, 4, 5, 6, and so forth. So the point out here is that in our initial test here, in the 1 month forecast, so the 0 month lead, so predicting October, starting October 1st, we're actually much improved versus CFS2. But if you go out to March, which is month 6, the skill is actually about the same. So there's definitely, again, there's that, because there really isn't any skill left that we can't even get, or there's other modern problems. But these are the things that we have to look into. And that's it's just sort of like show a flavor of the things that we're working on. And the summary is that NOAA is moving towards a unified forecasting system for all operational applications. And in all global applications, so GFS, GEFS, and the seasonal forecast system, and the hurricane analysis forecast system, which was that animation I showed you, will be fully coupled. But the coupled models provide more complexity and need to be evaluated across all components: ocean, atmosphere, land, etc. The UFS is an open source community developed model available at this link, and You'll have it in and I can share these slides. And there's also more information about the UFS modeling in this ufscommunity.org website. And I just want to put out there that the experimental forecast results, not the ones we have here, but the project starting in October 1st officially, all the data will be hosted on Amazon S3 bucket for the community to look at, evaluate, and hopefully feedback to us. So we know we could have more eyes on the model, we'll find more things, and hopefully, basically we'll make a better model and make better predictions. So thank you for your attention.
Questions?
So with respect to the last point, will the operational forecast products also be hosted on AWS?
Yes, they will be. The challenge right now is I think a lot of it is, but it's not being put up there in a call it a cloud-friendly format, and so it's not very useful. Like right now, because the WMO standard for forecast is grid files, and basically they're just putting grid files up in the S3 bucket, and they're not useful. We're planning on putting the data in the ZAR format and even the operational, so then people actually could use it.
Earlier in the talk, you showed a bunch of what appear to be the benefits of the stochastic physics that were quite substantial in some of those slides. And I guess I was wondering why exactly that was happening. Because I can understand it increases the variability, but you're actually shifting what appears to be the bias, results. So the only explanation I have is that the control run doesn't run it. The parameters used are so far off, and that you're just increasing the variability and getting
and you're finding hitting the right attractor once in a while.
I've never used stochastic in a bias correction sense. It's just to increase the ensemble spread.
Yes, we actually see this a lot in when we first developed it and looking at like the day 5 forecast. And yeah, the signal to improve the forecast, so not the bias, but actually reducing the RMS error was substantial in certain areas. It was almost as big as the increase in the ensemble spread, and never fully satisfying way understood why that is. And then same thing, like there's there's papers from my co-author colleague Judith Berner and other people in her group that looked at this and how the stochastic physics improves the spectra of El Nino. And it's interesting because in the CESM run, the El Nino is 2 biennial. It just goes El Nino, La Nina, El Nino, La Nina, just back and forth. And it improves the spectra to be more like observations, more like that 3 to 7 year period. On the opposite side, they ran it in the IFS, or the European Centers Coupled Model. Their El Nino was too infrequent. Stochastic physics made it more frequent, closer to observations. So it seems like, again, like if it doesn't matter where you're coming from, it's gonna bring you to where you need to be, and it's not satisfying, but it's it seems to be happening.
Kind of magical to me.
Yeah, and it's very suspicious, but I mean, it could be, yeah, because that we're just so off from the truth that this is, banging it around, and sometimes you fall in the right place, right?
Well, it tells me maybe that there's something hidden in there that you can get better parameters, physics parameters to start with, and then do the stochastic around that, where you might even get more improved.
Yeah, you're probably right, but I love to talk to you, and if there's any ways to tease that out, to figure out what those parameters should be, it'd be great. So.
An immediate follow-up of Brian's question. Can you tell us what parameters, what things you did to increase the stochastic?
So what we're doing, so one thing that's common between the two models, CSM and UFS, is called SPPT, where all we're doing is sort of dynamics runs, gives a state to the physics. Physics does its, changes the heating and so forth and the physical parameterizations, and returns a tendency back to the dynamics. And all we're doing is perturbing that physics tendency. we're doing a couple of things. We're doing a couple of detailed things where we're not perturbing the clear sky radiation, because we know when the sun goes up and down. We're perturbing the cloudy part, how the clouds interact with radiation, but we're not perturbing clear sky. That's, I think, the only thing we're not perturbing. Everything else is just whatever it is. The physics tendency comes in. We hit it from with a random number between 0 and 2, with some spatial and time correlations on it, and just return it. That's all we're doing. The UFS also has another piece in there called SCEB, which injects U and V winds into the flow in areas where there's a lot of numerical dissipation around, like cold fronts, any strong cyclones. The model's diffusion will basically tend to smear out those features. So what we're doing is just injecting winds to keep the energy levels the same. So,
Thank you.
yeah, so very simple.
More questions from the room? Yes.
Yeah, hi. At the very beginning, you showed a whole bunch of coupled modules that talk back and forth to each other. And I mean, it's a little scary, the number of those things. The question I really have is, how do you evaluate the improvement or deprovement of skill when you make a change in one of those modules? Bob Sess, who's the founder of this department, used to quote from the Alpha Romeo owner's manual that says, just change one thing at a time. And I'm wondering if you follow that in some ways. So you make one change in CMAC, for example, or whatever, and you look at the consequence of that over, say, a 20-year run, and you see what's the consequence of that.
We do that at some level. It's not as rigorous as we would like to. Like, for example, like we probably don't do a 20-year run. We do a much shorter test. But we also have there's this whole hierarchical testing framework where we actually, like, for example, if we're going to change something into the physics, like, change the convective scheme, we actually have a single column model that is just the column physics with prescribed surface, prescribed large-scale divergence, and we can see how does it predict observations at that level. So we go from there. We could build up to basically doing atmosphere-only experiments. Then we do fully coupled. We do all those pieces along the way for a lot of things. Now, the single column model only exists in the atmosphere. If you wanted to change something like the ocean mixing, we don't have a framework for that in that sense. In that case, we could do, and we do this, is that we run the ocean model with prescribed winds and prescribed fluxes and look how that evolves. And we do a lot of things in a data assimilation framework where we basically cycle the forecast model 6 hours, how does it fit to the observations, make adjustments. So we're always looking at it in how are we fitting observations. But looking at individual components like that, it's tricky for some of the things that we look at. But we always do something in that own component first before we do it a fully coupled model.
I see it very tricky because you have interactions between these different modules, and you change this one and that one in that module and this and that module. You're kind of in a narrow trough, and you can't say which is the better parameterization.
Mm-hmm. Yeah. And
very, very tricky.
Yeah. And the one thing I've struggled with some of the developers is that they always look at the result of what their parameterization looks like in the upper atmosphere, and they don't look at how it affects the surface, how it affects the fluxes. And think about even in an uncoupled run, atmosphere only, you want your fluxes to look like nature. And if you look at these runs, their fluxes are off by 100 watts per meter squared in some areas, and they're trying. That's scary. And they're trying to then tune their parameterizations basically to make up for this. The boundary layer is now too dry, and they're trying to adjust their parameterizations to it. It's like, no, the surface. You need to start at the surface and work your way up. So I'm working with them to try to look at that to basically. So then when we go coupled, we're not going to have all these problems. Then you don't know. All of the problems. Yeah.
Yeah, more questions from the room?
example, is there any plan?
Sorry, which one?
H-hubs.
Yeah, that will be set it on the slide. Sorry, what did it say? Oh, it is as of June. So yeah, so the current version that's running right now is fully coupled. It's not global. It's a domain over the Atlantic and Pacific Oceans, but it is coupled to.
Is it available for us to download and use?
Yes, this is actually if you were to go. So this is the nice thing about the unified forecast system is if you go to this UFS weather model, HAPS is there. It's all part of it, and it's just how you build the model. It's basically there's directions, and you just tell it I'm building the HAPS application, and it will compile it. Now you don't have all of the external files to run. That's in a different location, but there is a thing called a workflow that is, again, you go to GitHub. I don't have the URL for that, but you could download the scripts that will build the lateral boundary conditions, get initial conditions, do all that for you. That does exist and is publicly available. Welcome.
I got just one comment. So probably the 50-year wrong. You saw the drifting to the code by.
Oh, okay. And
but is that after the 20 years wrong, later 30 years or the?
No, it's pretty steady. I have made some time series, and it's a gradual drift. It's not like it's not like it's constant for the 20 years and then falls off or anything like that. Or it's a pretty steady.
Yeah, I'm just wondering whether that's related to the stop the increase of the CO2.
Yeah, it's not. Yeah, it's not.
Okay. Yeah, Jeff Gill has another ensemble integrations using their CM4 recently.
Oh, okay.
It's for several decades as well. I think these two sources will be good to compare with.
Yeah, it'd be nice to look at that because because also I like to talk a little more because because this is the 1 degree version that we really sort of just use for sanity checks that I decided to run because I've been told, oh, this is not a scientifically valid configuration, but they haven't given me one either. So
yeah, okay. We have audience on the Zoom. Do you have any questions from the Zoom?
Yeah, this is Edmund. Yeah, great. I have a question.
Now we will have lunch in the Swanson room by the library. Graduate students will have the chance to meet the speaker after that about 1:45 to 2:30. So let's thank Phil again. Adam, do you have a question?
Oh, yeah, I have a question. Can you hear me?
Oh, hold on. Can you speak up?
Yeah, can you hear me?
I can hear you now. I was sorry, I had it on mute. Sorry. Okay.
Okay. Yeah, I have a question. Now you showed some results about integrating this model to long periods of time. I'm just wondering why there's no plan to use this model to replace CFS v2, but actually develop a new model for that. I think you showed some results showing that the SST doesn't improve a lot, but the atmosphere model is definitely much better. For example, the teleconnections and stuff, for even GAPS 12 is better than CFS version 2, and GAPS 13 is probably, this one would be GAPS 13, would be even better. So the question is why wait another 4 or 5 years to replace CFS v2, which is a really good
question. And there are people saying we should just use what we have now. The challenge is to produce a good reforecast data set. We don't have initial conditions to go back 40 years to initialize this model in a consistent way. Now, I've done it for 30 years, but we're using ERA5 and ORS5 to initialize, which might be different than the operational system. So there's going to be discontinuity when you look at the hindcast versus the forecast. So most of that effort it's going to be doing is produce the reanalysis and the reforecast. So it's actually 5 years of developing a model. Really, in my mind, it's like we have a year to work on some of these biases, and then it's the reanalysis, reforecast. He froze.
Okay, thank you. Mhm.
Okay. Yep. You're welcome.
Any more from the Zoom? All right, I think
All right.
that's it.
All right.
Thank
Thank you.
you again.